Okay, so let's continue with Laplace's equation. So today we're going to finish it, this example. In R2. So last time so let me just jump into the problem. I'm not going to introduce it again, but so we had a boundary value problem, right, for the square. We had boundary data on all sides of the square. And then what we did is we broke it up into 3 or 4 subproblems, and then the sum of these solutions is the whole thing. Okay, so recall that we had we were on problem 3. Right, which had the following shape. Right, it was that it had 0 boundary data here inside the interior. This was 0, and then the Laplacian 0 here, and then here. So here's 0. Here's x is equal to 0, and here's x is equal to pi. Here, so this was. So we have to specify this for x, right? So this is x pi minus x. And so this is the line y is equal to 0. So restricted to this line here, we had this boundary condition. As you remember, we had general solutions for, we had solutions. So this is like the problem here with where we had data appear and this be 0, right? But it's just flipped, okay? And that allowed us to show that we had a solution of the form. We had this like general solution where we reflected things. We obtained the following general solution, which was k is equal to 1 up to infinity, and then we had some constants here. Sine of kx, kx, and then we had hyperbolic sine, and then we had k pi minus y. And so we set y tilde equal to pi minus y, and that allowed us to transform the equation. So we just need to get the boundary conditions, okay? So or solve for the ck. Using that, so x0 pi x minus pi, or let's see, x pi minus x. Right? So this is what we have. And to do that, we'll do a Fourier sine series expansion. Okay? So a sine series. So we have that x pi minus x. So this is the sum from k is equal to 1 up to infinity of, and then what we do is we use, so this is sine kx sine kx. And then here we have x pi minus x sine kx, like so, times sine kx. Okay, so we're going to solve for this. And what does this end up being? This ends up being, okay, so we'll call this thing sum k is equal to 1 up to infinity. Let's just call this ak sine of kx. Okay, and it turns out that ak, so this is the integral from 0 to pi of x pi minus x sine of kx dx divided by the integral from 0 to pi of sine kx squared dx. Okay, so the bottom one is pi over 2. And all together, if we integrate what the top one is, so this becomes 0 if k is odd. Okay, and then it becomes 8 over pi times 2j plus 1 cubed if k, or sorry, this is even 2j plus 1. Okay, so 0 if k is even. Okay, and so this tells us that we have the following formula, so that x pi minus x here, this is the sum from j is equal to 0 up to infinity of 8 over pi, and then 2j plus 1 cubed, like so. So we can just do this, 8 times 2j plus 1, sine of 2j plus 1 x. Okay, so this is what we get. And this is on the interval from 0 to pi. Okay, so it's kind of, so again, the hardest part of these things, or the most computationally expensive part, or I don't know what you want to call it, but one of the things that's kind of a pain in the butt to do is to compute what those integrals are. Okay? And this is what the answer is. Okay? And so now we can just solve for what everything is. So we get that sine k. So this tells us, so this thing is ak here. So we get that here. So we'll just write down the equation. So sine, so using this thing, okay. All right. The following equation, so we get the sum from k is equal to 1 up to infinity of ck of sine kx, and then we have hyperbolic sine of k pi, and so this is equal to this sum here, sum from k is equal to 1 up to infinity of sine ak sine of kx. We could write out what ak is if we wanted to explicitly, but this tells us here that ck, so we have two vectors. They're written in terms of a basis, and so we just get to equate the coefficients. Okay, and so this tells us that ck is equal to ak over hyperbolic sine of k pi. Okay, and this allows us to write down the complete solution of our equation here. All right, so here, so we only get this part. So we only get the odd terms. So this tells us that psi 3 is the sum from j is equal to 0 up to infinity of 8 over, so now we're just going to do the same thing, pi 2j plus 1 cubed. I guess we can extend this, hyperbolic sine 2j plus 1 pi. So that's the coefficient. I guess I can write the 8 here. And then we have to multiply by the two functions, which is hyperbolic sine, or sine of 2j plus 1 x. This whole thing times sine hyperbolic of 2j plus 1 pi minus y, like this. Okay, so we get this series solution here. Okay, so this thing is just multiplied by that. Okay. Okay, so that's what we have for this solution here. So for problem 4, is a very similar situation, except for we had on this side, we had some unspecified functions, 0, 0, 0. Okay, so this is problem 3. With x and y flipped. And so we can do the general solution. So we got to do the general solution here. So we get, so from these two boundary conditions plus this boundary condition, okay, so we get psi 4 xy. So we have something like sk is equal to 1 up to infinity, ck, sine of ky now, hyperbolic sine of k pi minus x. Okay, so we would do like an x tilde here, and then we would show that the Laplacian of, so x tilde is pi minus x, and then we would do the change of variables for Laplacian, show that it's still a Laplacian in the new coordinates, and show that that it would switch the data from here to here, right? So we would have something exactly like, I forget that maybe this was problem 2, right? Except for with this change of variables for x. Okay, so now we just need to match the ck's with the data here. Okay, so to solve for ck's, we use a sine series or eigenfunction expansion of f of y. Okay, so we'll write f of y. So this is what it looks like in general. So we can write from k is equal to 1 up to infinity of ak sine of ky. Okay, and then here ak is like what we have before. So except for now it's on the y plane. So ak. Here ak. So this will be f like this. Ky like this. And so this thing's just the integral from 0 to pi. Ky dy over 0 to pi sine ky squared dy. Okay, so we have these coefficients like this. Okay, and so the bottom one is pi over 2. Okay, and so, all right, so this allows us to equate okay, and so we can't really do that in general, but we can still write down the equation, right? That psi 4 here of, and so this is at 0, x is equal to 0, y. So is equal to this series here is equal to f of y. Okay, and so it doesn't give us this equation, but it'll give us this equation here, which says that the sum from k is equal to 1 up to infinity of ck sine of ky, and then we have hyperbolic sine of k pi. This is equal to the sum from k is equal to 1 up to infinity of ak hyperbolic or sine of ky. Okay, so we're using that sine series expansion of f, and so we have the equality of two vectors, and so we just get to equate coefficients. Okay, so they're written in terms of this basis. Okay, so this tells us that ck of pi or k pi is equal to ak, which tells us that ck is ak divided by sine hyperbolic of k pi. Okay, and so therefore we get our solution. Our solution is that psi 4 xy is the sum. So it's just like here, we're just like writing out all these details, but we go through, and the idea is you get the form of the solution from some of the boundary conditions, and then you just match it up to the data by doing a sine series expansion. Okay, so we have ak over hyperbolic sine of k pi, and then we have sine of ky over hyperbolic sine of k pi minus x, like so. And so ak will be something explicit if you were to pick a particular f. All right. Okay, so we have all the solutions that we have. We have all the solutions for problem. We have the solutions for problem 1, problem 2, problem 3, and problem 4. Okay, this is the solution to problem 4, and now we can put them all together to get the full solution. Okay. So the solution. Okay, so psi okay, and so the solution of the first problem was, so this is I hope that you guys can see that this is truly a nightmare, right? Why? This is our first problem. Then we had 3/4 hyperbolic sine like this. Okay, let me just invade this space here. All right. This is the third one. It was 8 over pi 2j plus 1 cubed hyperbolic. So this is also in, I think, 5.2 of Snyder's book, right? So you'll find this exact example. Oh, sorry, this is in the denominator, huh? Okay, this term, then we have the hyperbolic sine term. Okay, then we had this like general thing. So we had k is equal to 1 up to infinity. We had this ak, so this was the coefficient coming from f that was unspecified. Hyperbolic sine of k pi, sine of ky, hyperbolic sine k pi minus x. Okay, so like gross, right? It's not so gross if we were going to do an abstract example. I mean, because all of them would look like this to some extent with the different. So the important part is like, right, we have our basis, what the bases are on each stage. Okay, so this was, I'll let you guys catch up for a second, then we can chat about this. Okay, so so the important part here is that you can see that the basis changes here. So this was like the first one we started where we had boundary data except for the top, right? Or I guess except for the x side, right? And then same thing here, but for the top of the, now this one was the top, right? Or let's see, actually, this was the sine cubed one, so this is the side. So this term, this one corresponded to this side, right? This one here corresponds to the data that was given up here. I think it was just sine of x was given there, and it was 0, 0, 0 here. And then here, we flipped it. So this was like 0, 0, 0, and then we had x pi minus x. And then here we had everything 0 except for some unspecified function here. That was like this. Okay? And so the important thing to notice is that what the shape of the functions were that we expanded in terms of, right? And then how we got these. And we got these from the sides that were all 0. So we did separation of variables, and we got they were all 0. And then we also used symmetry to reduce some of our problems to the previous problems. Okay? So that was the idea. And so in general, these things look kind of gross, right? If you were just going to put some random functions in there. But they're all really sums like this, okay? Where these are the coefficients. So these things were the sine series coefficients for this expansion, right? The coefficients here are the sine series expansion for this one, and the coefficients here are the sine series expansion for this one. The coefficients here are the sine series expansion for sine, right? Divided by this other term that we got. Okay, that's the idea. Okay, so any questions on this? So I think you guys are ready to go and do an example like this, right? So for some sides, and you can play with it. If you were going to add, instead of these boundary conditions, if you're going to add like a derivative of your function here, right? So this is like psi 3. You'd get a cosine series expansion instead of a sine series expansion. Okay? Okay. So, all right. So let's move on from this thing, and we'll do some more separation of variables. Okay. So one thing that I wanted to mention was what happens when so when we change coordinates and we don't have this, so remember we moved to this u tilde one time. And it turned out that the Laplace equation in these new coordinates is the same, right? But we can try and do is we can change coordinates in another way. So if so let me show you what happens in polar coordinates. Okay? So this equation okay, so here x, we can use this transformation. Or we could use that equivalently, we could use that theta is inverse tangent y over x, or we could use that, r squared is equal to x squared plus y squared. Okay, so we have these two ways to change from Cartesian coordinates to polar coordinates. Okay, and the way that we convert these partial differential equations into different coordinate systems is we have to use the chain rule. So okay, and there's kind of two ways to go about this, and there's kind of a conservation of pain here. Okay, doing these things, kind of like writing these things, is if you write them down in concrete terms, they get kind of ugly. All right, but let's write down our two options, and then I'll go through the two options. We don't have time to finish the change of coordinates today, but I'll go through it one class. And I'll tell you what the answer is. So let me tell you what the answer. So here was our question. All right, so this is our question. The answer is the following. It is that it looks like, okay, so d squared u dr squared plus 1 over r du dr plus 1 over r squared d squared u d theta squared. Okay, so this equation is the same thing as this equation, but written down in polar coordinates. Okay? And what we do is we have to use this, to get here, we have to use the chain rule. Okay, so let me tell you what the chain rule is, just a reminder. Okay, is that, so we could use this one. D theta dy. So we have this system of equations, or we can use another system of equations which is related to this one. Right? It's that, or so what did I do? Let's see, du dr. All right, and then we have theta plus Okay, so we can start to do these, and then we'd have to do, so what we'll have to do is we'll have to do double derivatives, either using that formula or this formula, right? So you have to decide whether you want to get things in terms of thetas or in terms of x's, right? And then you have to use these identities here, okay? So we'll have to do that kind of like, we'll have to do second derivatives, so we'll have to apply this chain rule twice, okay? And then we'll have to be able to take certain partial derivatives using these formulas and then substitute them in, right? This becomes a mess, okay? So it requires us to be organized. And then once we make these substitutions, we do the second derivative, this thing will pop out, right? It's kind of like one of these things where like everything cancels and it becomes nice, all right? So it's kind of like when if you've ever computed how the change in coordinates for spherical coordinates or something like this, and you just get like this rho squared sine phi type thing, okay? Or like r d theta. This is what comes out when you change the area element and when you're doing multiple integration. Okay, so if you've done those computations where everything cancels out, this is the same idea. Right? Everything will become nice. Okay, what I wanted to say now is that when we do this, some of the equations, okay, so let's take this equation for granted and we'll come back to this. Okay, so we're going to take this for granted. The idea is it comes from the chain rule, and we'll come back to that next class. But what we can do now is we can try and separate variables here, okay? So this equation, so the polar coordinate version is helpful when solving boundary value problems. For a disk. So here, you could specify, right? So here you could have some disk here, or you could translate the disk. Right? But let's say it's a disk at the origin in R2. And then you could say at some radius here, you could say that, so you could say that you could look for the problem and say that the Laplacian squared of u is equal to 0 on the interior of the region. And then you could say something like u restricted to, say, a circle, the boundary of the circle, when r is equal to some fixed r naught, you could say that this is some function that depends on theta. So this is boundary data here. So this is what's called the Dirichlet problem, is if you take any region here and you specify the boundary, right? The boundary data, you'll get this Dirichlet problem, right? And we'll try and solve this. Okay, and to do this, we're going to separate variables, but we separate with respect to r and theta and not x and y. Okay, so we're going to have something like this for let's say inside the disk. Of radius r naught, and then we could say that u of r naught theta is equal to f of theta. So this is the boundary condition. Boundary. Okay. And to do this type of problem, we're going to separate variables. Okay, so the first step okay, and so what we're going to do is we're going to do a superposition again of these separated solutions. So u of r theta, we're going to write as r of r, theta of theta. Okay? And so then we put this back into our equation. So we put this into the Laplacian. right? And so this equation here, so this is the same as, okay, so what do we have? So we have u of r. Okay, I'm just going to copy it down one more time just to be clear about what this equation is. U of r plus 1 over r squared u of theta is equal to 0. Okay, so this is the Laplace, this is the same equation here, but we're just using different coordinates. And now we are going to plug in our solutions. So we get r prime prime, right? So when we put this into here, right, we get r prime prime theta plus 1 over r prime theta plus 1 over r squared r theta prime prime is equal to 0. Okay? And so if we divide by r and theta, okay, so to do that, we do this and we get r prime prime plus 1 over r prime. Okay, this thing divided by r plus, I guess we get 1 over r squared theta prime prime over theta is equal to 0. Okay? And so this equation tells us that r squared r prime prime plus 1 over r prime divided by r is equal to negative theta prime prime over theta. So this term here depends only on r, on little r. And this thing here only depends only on little theta. Okay? And so the equation we get is the following. This tells us that r squared r prime prime plus 1 over r prime over this thing, this is equal to some constant here. So lambda is some constant here, and we get minus theta prime prime over theta is also equal to lambda. Okay, so when we separate this out, so we'll get the two equations here. So what do we get? So we get that r squared r prime prime, okay, plus r prime minus lambda r is equal to 0. And then we get, or we could say this is equal to lambda r. And then we have, let's write it like that, because it looks more like an eigenfunction. Because we have some operator here, and it operates and it spits out this function lambda times r. And then we also have that theta prime prime here. This is equal to, so let's do the negative theta r, or negative lambda theta, like this. Okay, so depending on whether we choose plus or minus lambda, we get these two, well, we get a plus or minus here, or plus or minus here. Okay, so this one's really the harmonic oscillator. Okay, and I believe this one is the Laguerre. So let me check. Oh, Laplace's. So I guess this is Laplace's equation. I have to check. So this is Laplace's ODE. It would make sense that it comes from the Laplacian, right? So I need to check. It might be the Laguerre equation. So these things, these ODEs, okay, so let me tell you that these ODEs that come from separation of variables, so you maybe have seen these from your ODEs classes, but these are like favorites because they appear as separated, they come from separation of variables from certain PDEs in higher dimension. So like, you know, we could take the Laplacian in 3D now, right? And then we could convert it to spherical coordinates, separate variables, and then when we separate variables, certain special ODEs will come out. And those are near and dear to our hearts, and we give them names, which I forget, right? But this is Laplace's ODE equation, you know. So he has two things named after him. Okay. So all right. So this is how we separate for this one. Okay. So we'll go back. We're going to solve these ODEs, right? But now we need to solve them subject to these boundary conditions. And now it's not going to be so simple. So you see now we have like an order 2 equation here, right? With non-constant coefficients. And these are where this is why we have to deal with this non-constant coefficient situation. It gets more complicated the more we do. Okay? So let me show you what happens to Laplace's equation in 3 dimensions without changing coordinates. So we have a good case, so we can have another example of how this works in 3 dimensions. Okay, so there's kind of like 2 levels of complexity that can happen. One coming from change of coordinates, which is described by this, and another one by adding dimensions, which is I'm going to describe by the following equation. Okay, so okay, so let's do Laplacian in 3D. So this is the equation here. So this is still a scalar, right? So this is this operator, okay? And so we will want to separate the equation here into using, let's say, using u of x, y, z, x of x, y of y, z of z. Okay, so we're going to do 3 of these. Okay? So if we put this into our equation here, so this is this thing. So if we put this into star, and so this is the type of thing you want to do if you have a box in 3 dimensions. Okay? If we have a sphere in 3 dimensions or a cylinder in 3 dimensions, we're going to have to go through something like this. Okay? But for a box in 3 dimensions, we use this. And so into this equation here, it gives the following. It gives that, so we'll have x prime prime so we have this equation here. Okay? And so this tells us that here, this is equal to 0, okay? Or it tells us that x prime prime over x is equal to, well, let's say minus y prime prime. So here I divided by x, y, z. Okay, so this thing only depends on x. And this thing only depends on y and z. Okay? So something that depends on x and y and z means that it must be independent of both things. So it must be equal to a constant. So therefore, so there exists some lambda complex number such that we have the following 2 equations, right? And we have that minus we have something like this. Okay? So from the second equation, let's call this dagger. Okay, we'll separate out the second equation again. The following, so let's write it like this: y prime prime over y plus z prime prime over z. That's minus lambda. Okay? And so this tells us that y prime prime over y, so this is equal to minus z prime prime over z minus lambda. Okay? So this thing only depends on y. On y. This thing only depends on z. On z, right? Little z. Okay? So this tells us that y prime prime, and these two things must be equal to some constant. There exists some mu in C such that the following equation holds. Y prime prime over y is equal to mu, and negative z prime prime over z minus lambda is equal to mu. Okay? And so this gives us the following set of equations, right? So this tells us, okay, so putting everything together, right? So we'll get that x prime prime is equal to lambda x. Y prime prime is equal to mu of y. And z prime prime. So I guess we can multiply this both sides by negative, and then we have to bring this over so we get negative negative, right? Is equal to minus mu minus lambda z. Sometimes we give this another name. We'll call that nu, and then we say lambda plus mu plus nu is equal to 0. Okay? So we have those equations here. Or sometimes we write it as nu so we have x prime prime is equal to lambda x nu z lambda plus mu plus nu is equal to 0. Okay? So we can separate variables, and then now we have the eigenvalues for these things are subject to this additional condition, right? That their sum is 0. Okay. So we've kind of seen what happens in two cases. One, if we change coordinates, we get more complicated ODEs coming out with non-constant coefficients. And this is what this general Sturm-Liouville theory is for handling those type of things, right? The other thing that we get is if we go to higher dimensions, we have to separate and we get more constants out that we need to solve for, more eigenvalues, right? But they're subject to an additional constraint that their sum is going to be equal to 0. Okay, so this is the kind of two types of things that can happen, right? In the next class, I'm going to show more details on how to convert one of these equations into a different coordinate system, okay? And then I guess I wanted to remind you that the redo of the quiz is on Friday. Okay, and so also try and do one of the Laplace's equations for this. Go look at the exercises for Laplace's equation on square domains and try and do some of those. And then maybe we'll have a quiz on that on Monday. Okay. All right. If you have any questions.